Okay, people, let's begin. Others can join us. So this is where we stopped yesterday on for EPR. Any questions on EPR or anything else in any aspect? You're all fine. Good. Okay. To recall, there's a spinning electron that we're looking at focusedly. Only thing that we're looking at now. We are applying an external magnetic field. The spinning electron has a magnetic moment, therefore it will align its magnetic moment either with the field or against the field. And it so happens that those two alignments have different energies associated with them. And if you provide energy which exactly equals the difference in energies between those two states, then resonance sets in. The electrons in the lower energy state will absorb the energy that's provided and move to the higher energy state between these two levels. And of course, a lot that coming down, going up happens. It's a stochastic process and so on and so forth. But simplistically speaking, that happens. If we can measure that energy, that can be used for a lot of purposes, or rather a couple of purposes. One is to identify, the other one is to measure the concentration. Okay, that's the basic thing. The energy is of the order of 10 power minus 3 kilocalories per mole. Therefore, it is orders of magnitude less than the energy associated with chemical reactions. Okay, so that's what we looked at earlier. So as mentioned, this energy provides the basis for the EPR spectroscopy. So under resonance condition, we already know that delta E equals GBH, and R just means the resonance condition where it can absorb. And of course, E equals h nu. Therefore, you could write this as a product of the Planck's constant. This doesn't show up, is it? Oh, yeah. The Planck's constant and the frequency at which the resonance is occurring. Okay. So that is straightforward. You might want to write these down, simple relations. Therefore, you could write nu r by hr. I'm just looking at the last two parts of the first equation. Nu r by hr equals gb by h. Okay. G, as you know, is the electron splitting constant. Therefore, that's a universal constant. Beta is a constant, right? And Planck's constant. So these are highly constant, and therefore the ratio of nu r by hr happens to be a constant. Okay. This brings about a very interesting view to the conduct of EPR spectroscopy. Okay. Typically, what do? You change your frequency, right? While measuring the frequency, wavelength, you change. And in this case, you have an energy, the magnetic field associated also in the whole process. Okay, the magnetic field is superimposed on the electron here. But what we do here is something else. For the resonance condition, all we need is the ratio of nu r by hr should be a constant, right? Therefore, the actual value of nu r by hr doesn't matter. As long as the ratio is a constant, resonance will occur, right? So, in principle, either nu r or hr can be varied to provide the resonance conditions, right? The typical or the traditional way is to vary nu r, the frequency, right? In this case, okay, let me tell you that a little later. It so happens that all EPR spectrometers operate at a fixed frequency, but change the magnetic field, okay, which is somewhat different from the way a traditional thing is done. You don't vary the frequency at all, you vary the field strength, because it's easier to vary the field strength than to vary the frequency in this regime. Okay. And yeah, we'll get to what frequency and things like that a little later. So this is the basis. You have a fixed frequency and you vary the field strength. When you do that, the energy absorbed with the field strength gives you all the information that is needed. That is what is measured. You measure the energy absorbed in some way. So the absorption spectrum will look typically like this standard, right? If you take the derivative of the spectrum with respect to H, it is going to look something like this. Right? You all know this. So you have somewhere till this point, you have an increasing slope, and then the slope decreases, becomes 0 at this point, and then the same thing happens. Okay. So the derivative spectrum of a typical absorption spectrum will be something like this. Okay. So both these are used, as will become clear as we go. Any questions so far? Everything is clear? Okay, you might want to just trace these out. This is the absorption spectrum. This is the first derivative spectrum with respect to H of the energy, absorbed energy. In the lab, magnetic fields of up to 15,000 Gauss are obtainable. Okay, you may need some specialized equipment, but 15,000 Gauss is possible. And to put some numbers to what we are looking at. So if you calculate the frequencies for resonance, it will be in the microwave region, which is about 42 gigahertz that we're talking about. Okay, gigahertz, therefore in the microwave region. So you have EPR spectrometers working at a fixed microwave frequency and varying H. H is varied with every operation. Typically, frequencies in the 9 to 10 gigahertz range are used for EPR spectroscopy, and there is a certain designation for EPR spectroscopy based on the frequency that is used. The S band uses a 3 gigahertz frequency, X band a 9.5 gigahertz. That's what we mean by 9 to 10. A K band is slightly more sophisticated. You can do its capability is more, that's 23 gigahertz. Q band is 35 and W band is 95. Okay. The one in our safe is typically a K band thing. I think it can do a Q band, but I'm not too sure about the reliability there. W band is very rare. Okay. People normally don't look at S band, X band maybe to a certain extent. K is common, Q maybe, W rare. So that is the frequency at which the EPR spectrometer operates, the fixed frequency. If you want to write it down, you can, but yeah, this is available. You do a search. This is from a book by Borg in 1983. Okay, fine. So when the energy matches, principle is simple. When energy matches, there is absorption of when the difference in energy level matches with the energy that's provided, there is a jump, right? And of the electrons in the lower energy level to the higher energy level, that energy is measured and processed to get information. So far, we looked only at a spinning electron. Okay, we said a spinning electron brings in magnetic moment that aligns with the field or against the field. You also realize in a classical view, the spinning electron goes around the nucleus, right? So in addition to this motion, there is a circular motion. If there is a circular motion, there is a moment associated with that also, in addition to the spin, right? That is one. The other thing is that this is spinning, this is negatively charged, there is a nucleus that is positively charged, therefore nothing prevents its interaction with the nucleus. Right? So that can further change the magnetic moment of the electron. Although we are looking only at the unpaired electron, all these contributions come in. Some of these contributions, all these contributions are important. That's already present in the system, and that needs to be taken into account. Okay. So the other contributions that could be important are as follows: an orbital angular momentum due to the motion of an electron in a circular path the classical view. Interactions with nuclear magnetic moments if present, and these interactions are called nuclear hyperfine interactions. So, nuclear magnetic moments may not always be present. It's present only in certain nuclei because of the way they are made up and so on. Okay. So, this first aspect is rather easily managed. I mean, we need to take care of it. It is managed a certain way. The second aspect needs a lot more doing to manage. So, the first aspect is handled by using an effective G factor or effective G value or a G factor, which characterizes the molecule in which the electrons are located. Okay. So, essentially, if you look only at this, there is a universal constant G value. If you look at this and this, you can talk of an effective fudge factor, I mean effective G value. Okay. So, that has been done, a G effective or a G factor, and many times there is no difference made between the spectroscopic constant, universal constant, and this G factor. It's just written as G. Okay, but you'll have to figure out what is meant. So, G effective or G factor or G is nothing but you just equate it to h nu r by beta hr from this relationship, and then you're all fine. Everything else will follow. Already taken care of. This the magnetic moment that comes in due to the circular motion also. This G factor, as mentioned, is not the G value, which is a universal constant. And to add to the confusion, many times that difference is not made while writing. You'll have to make out the difference. But once you get used to it, it's not a big deal. You can figure that out. Okay. This is just to, you don't need to write this down. This is to give you an idea of the range of values for a class of compounds, for different classes of compounds, for the chlorophyll and so on and so forth. You have 2.0024 to 2.0028. That's the range in which you're looking at the G effective factor or G factor, and so on and so forth. Okay. If you recall the value of the electron constant, spectroscopic splitting constant, it's 2.002319278. So, you find that it is pretty much in the range. So, that is good enough to take care of the variations. So, it's all pretty much around that. But in those calculations, these numbers will make a difference. So, you'll have to use the appropriate G factor. Okay. This is also from Borg. If at all you're going to work with them, you need to go and figure that out. The second aspect is the interaction with the nuclear magnetic moment. And of course, that, as mentioned, it is much more involved. Something like this. Please follow this discussion. Once you get this, then jump is quite easy. This is a plot of energy versus, okay, I need to get here. Okay, energy associated with the process absorbed and so on and so forth, versus the magnetic field strength. You know that the magnetic field strength is varied. Typically, in electromagnet, so you vary the current through it. The magnetic field strength varies. Okay. For if the electron has a negative half spin, then the variation is typically like this. This is for a single spinning electron. If the electron has a positive spin magnetic moment, this is a magnetic momentum number, right? So, the variation is something like this. At the condition of resonance, this difference would be G beta HR. Okay, this is the HR at which resonance occurs. The difference between these two energy levels is going to be G beta HR, that's your delta E. Okay. So far so good, figure is fine. Okay. And this is what is measured, the energy absorbed to go from here to here during the measurement. Therefore, the energy spectrum, energy absorption spectrum is going to look something like this. The derivative spectrum is going to look something like this. Typical, the classic spectrum. That is fine. I see some blank faces. What is wrong? What is not clear? Yeah. This is variation with H. Okay, this is the energy level. This is not delta E. This is energy level. Okay, energy level variation with the magnetic field strength applied is decreasing in this way if the electron has a negative spin value, and increasing if it has a positive spin value. At the resonance, whatever the difference is between this and this, okay, it goes from the lower energy. Okay, if it is aligned with the field against the field we mentioned, right? If it is aligned with the field, it will have this energy. If it is aligned against the field, it will have this much energy. Okay, so if this difference is matched by your HR or H, then it will switch. Only then will it switch. Otherwise, it's not going to switch. That's what it means. Anything else that is not clear? There's essentially a so far we have been looking only at the delta E. Now we look at the energy variation with the magnetic field strength, and that particular point is what we were looking at earlier, nothing else. Any other? I still see a lot of puzzled faces. No? You're all fine? Something is not right, but yeah, probably you don't know what is not right. Yeah, you'll figure it out. Okay. Only if I know what is not right can I fix it. Otherwise, it's difficult for me to fix it. I'll at least try to fix it. In this case, if you introduce a nucleus, in this case, let's start simple. We'll introduce just a single proton. Okay. Into the overall picture. Okay, the proton is also spinning. It will, I mean, proton has a net magnetic moment and so on and so forth, right? The nucleus of spin I, let's say nucleus of spin I causes the split in the energy levels. What do I mean by this? It brings into existence more energy levels. It will not be clear until I show you this. Okay. What happens is, you look at this dotted line, those are the initial values that we talked about in the absence of the electron, sorry, the absence of the proton. The electron energy levels in the absence of the proton. Now you bring in a proton, one proton. What will happen is, because of the interaction between them, between the magnetic moments, you will have the variation in the energy of the electron with the magnetic field strength for the electron minus half and proton minus half going like this, the proton plus half going like this. This is the nuclear magnetic moment number. Okay. Similarly, this, in other words, this one level has split into two levels, possible levels. Okay. So, and if you look at the electron with a positive spin, then because of its interaction with the nucleus with a positive or a negative spin, you are going to have one variation which is here, the other variation which is here. So, these are the four energy levels that become possible. Okay. Whereas the difference between the thing is this, these no longer exist. However, the difference is the same at this point as well as at this point. Okay, it's an optical illusion which makes it look something like this. It's exactly the same. They're all straight lines that I've drawn it with. Okay, so this delta E has become possible at two different HRs or Hs, let me say. right. So, this no longer exists because of the proton has come in. Instead, this has become possible and this has become possible. It will switch here, or in other words, it will switch at this value of h as well as at this value of h, because the resonance condition is matched there. Any question on this? Okay, all this is classical view. Okay, so it will be reasonably consistent, but it will not be. You cannot extend it and so on and so forth. So you cannot use it so well, but good to understand something. So this is what happens. In other words, one energy curve or one energy spectrum, energy absorption spectrum, has split into two. So bringing in one proton has split the initial one energy level into two energy levels. So the nuclear spin interactions cause more number of electron energy levels of the same energy difference to become available for transition, or a split in the electron energy levels happens, or the nuclear spin interactions split the electron energy levels. The splits in energy levels are called the hyperfine splits, because we said hyperfine interactions is the name that's given to the interactions between the proton magnetic moment, electron magnetic moment and the proton or the nuclear magnetic moment.
So due to the split in the energy levels, will we get different values of delta E so that?
No, we don't get different values of delta E. We get the same value of delta E at different edges.
At different HRs.
Yeah.
So
HRs increase.
do we need to like mean of those HRs?
No. We don't do that here. Hold on. I'll tell you something that we can do. Beyond that, you need a quantum view to use that. I haven't completed this. Okay. So we'll finish this part of it. Each nucleus of spin I splits the electron energy levels into 2I plus 1 sublevels. You can work this out and so on and so forth. However, note that only some nuclei possess a net magnetic moment. For example, 12C and 16O do not possess a net nuclear magnetic moment. So, if you are dealing with 12C and 16O, then you do not have to worry about the interactions, the nuclear hyperfine interactions at all for that molecule alone. Okay, this is only for a molecule. If you, in the compound, there will be so many other things. At least the nearest neighbors will matter. So, therefore, the nuclei of 12C and 16O will not split the electron energy levels, whereas 1H, 2D, okay, this is the deuterium, 14N, 13C and other nuclei that possess a net nuclear magnetic moment will split the electron energy levels. You might want to write this down. 12C and 16O will not split the energy levels, whereas this is just an example. There are many, 1H, 2D, 14N, 13C. These are most common, of course. There could be others also.
So unlike the isotopes of C and O, the isotopes of H can split.
Yeah, no, we don't know that. I'm not saying that. I'm not saying anything about the isotopes. Here, these 12C is standard form, 16O is a standard form, 1H is a standard form, 2D is of course an isotope. As 14N and 13C is a isotope, yes. 12C is standard, 13C is the same. I wouldn't extend it in general. You'll have to check whether each nucleus possesses a net magnetic moment to interfere with the electron magnetic moment. Yeah. NMR 13C, typically 13C is a very common thing. They follow 13C in NMR and so on. Principle is exactly the same, but the way they process it is different in NMR. NMR and EPR are very close in terms of the basic principle. They look at nuclear magnetic moments. We are interested in electron magnetic moments. That's essentially. Okay, that's why this is electron paramagnetic resonance and electron spin resonance. Electron spin is only this. Electron paramagnetic resonance is this and interactions with the nucleus all included.